Okay, round two, we'll pick back up at number 8 in this part 2 for the chapter 3 test review. Number 8 says determine the end behavior of the graph, which means you're going to want to look at the leading coefficient, which is a positive 8, and then a degree. So we know if you're an odd degree, your end behavior is split. So one is going to be heading up and one's going to be heading down. And we know if it's an even degree, then they'll both match. So they'll both be heading up or they'll both be heading down, depending on what the degree is, the sign of the leading term is. And since this is a positive, that means we're going to be heading up from left to right. So this is our winner right here. It looks a lot like what we saw in number 7. And so as x goes to positive infinity, y is going to be going to positive infinity. And as x goes to negative infinity, y will be going to negative infinity. All right, so as x gets bigger and bigger, y is going to get bigger and bigger. And as x gets smaller and smaller, y gets smaller and smaller. And so that's what they're looking for when it comes to end behavior of the graph. Number 2, we are going to find an appropriate model for the data in the table. So I already went ahead and put this data into my stat edit. L1 is my x's, L2 are my y's. And then you have to make sure that your stat plot is on. So if this says off, you have to hit enter. And then move Blinky onto the on and hit enter so that it looks like this. When you hit graph, you're probably not going to see anything, so you have to go to zoom, stat, or z-stat, and then you get a picture that kind of looks like this. And so it looks like we're starting right about here and just heading down. And so I would say that this looks like a quadratic, that there's only one turning point. And you can't even really see the turning point in this table right here. So I would say an appropriate model, given this, is most likely going to be a quadratic. So I'll go to the main screen, go to Stat, over to Calc, and pick Quad Reg. And I want to go ahead and put this into my Y1 without having to change anything up. So I'll say second 1, comma, second L2, comma, vars, over to Y vars, function, and then Y1. And when I hit enter, it will put it on the main screen, but it will also put it in Y equals. So when I hit graph, well, that looks pretty good. I think we have ourselves a winner. And if you weren't so convinced, what you could do is go in and maybe run a cubic and do the same thing. L1, L2, of course, well, I'll go ahead and put it in Y1 again. I was going to say I'll leave it in L2 so I can see both, but I think this will be good. Oh, look at that. That's much better, actually. I'm glad that we looked at that. So it looks like our our cubic model is much better, actually. Round to the nearest thousandth. Oh, goodness, I got a point, negative 0.005 x cubed, 134x squared, negative 1044 x, and then a 50071. I would say that I would take either the quad or the cubic, mostly because judging by this, I don't see any other turning points. So I think it would be reasonable to think that the quad was your best fit because of the lack of turning points that you see on the actual chart. But there's certainly no denying that the quad, the cubic rod fits the model better. 10, use synthetic division and remainder theorem to find out what you get when you have a negative 1. Now you can certainly go ahead and just plug negative 1 in, but it is probably going to be faster to use the synthetic division. Because it says use synthetic division, that's what I expect to see. Line up your coefficients, make sure there's no skips. So I got 2, 1, none. So I'm going to put 5, 6, 4. Drop the 5, and now it's negative 1 times the 5. Put the product underneath here. Add down. Do it again. Negative 1 times a positive 1 is a negative 1. Add down. And P of a negative 1 is a 3. So if you plug in a negative 1, you get out a 3. Kind of going to use the same idea for factor theorem, but we want this last number here, or remainder, to be a 0. Now when you look at this, you can check all of them using the rational root theorem, but what we'll do is we'll go into y equals, and I will clear all this fun stuff out, and I'll put in x cubed plus 6x squared plus 9x plus 4, and I will hit graph. And I have all kinds of stuff floating around, so I'm going to do zoom standard and just kind of ignore the dots for a minute. And it looks like I have maybe a negative 1 and maybe, what's that, like a 4? So let's go into the table. Oop, negative 1 is certainly a winner, so is the 4. So let's see. I can use either one of those. I think the answer key uses the negative 1. We'll do both. So if I was going to use the negative 1, I would put this in here, line these up. I have no skip, so I don't have to worry about that. Am I going to be able to scroll down? Yeah. Drop the first one, and I have a negative 1, add down. Multiply, add down. Multiply, add down. He's a 0. So that means not only is negative 1 a root, but x plus 1 is indeed a factor. And x plus 1, your divisor, times your quotient, which is going to be x squared plus 5x plus 4, is equal to that. So that's just another way to say the p of x. If we chose the negative 4, we would do the exact same thing and get out x plus 4. And then in here, we would let's see, what would we get? X plus 1, and it looks like another x plus 4, which makes sense because you can see this tag right here. Oh, another x plus 1. Another x plus 1, because that tag means that he's a multiplicity of 2, maybe even a 4, but we know this guy's cubic, so that would be a 2. So either the x plus 1 or the x plus 4 would be fine. Come back here. Find a polynomial of degree 3 that has the zeros 5, negative 5, and 8. So I have x, well, let's start this way. I have x equals a 5, x equals a negative 5, and x equals an 8. That came from x minus 5 is equal to 0, x plus 5 is equal to 0, and x minus 8 is equal to 0. Gather up the expressions on the left. I'm going to swap my x plus 5 and x minus 5. And I got this x minus 8. Normally I start with these last two, but since I know that this is the difference of two perfect squares, I'm going to rearrange the order a little bit. Put the x minus 8 out here. And put the x plus 5, x minus 5 in the back. So when I multiply these two expressions together, this is going to be an x squared minus a 5x plus a 5x minus a 25, and these add out. So now I just have to multiply the x minus 8 times the x squared minus 25. If you left it like this up front, that you multiply the x minus 5 and x minus 8 and then sent the x plus 5 through, you're going to wind up with the same answer. Just you're going to have more terms at the end to have to combine. Let's send the x through. That's Abby barking. I got an x cubed minus a 25x. And then send the negative 8 through, negative 8x squared. And then 8 times 25 is 200, and negative times negative is a positive. And I can put that in the correct order. I'm kind of out of space, so I'm going to head this way. That my polynomial that I'm looking for is x cubed minus 8x squared minus 25x plus 200. And that would be the one I'm looking for. Number 13, I want to find a third degree polynomial whose graph I see below. It's very important that they say third degree, because then that tells you how many times these multiplicities happen. If they didn't say third degree and they just said, like, find a polynomial that you think might fit this, a third would certainly work, but so would, let's say, 1, 2, 3, 4, 5. So would 1, 2, 3, 4. There's a couple of different ways depending on the multiplicities. This is a tag, so we know he's even. So this would be 2 times or 4 times or something like that. This is an odd, so this is 1 time or 3 times. And now since I know it's a 3, I can restrict that a lot more. I know he has to happen twice, and he can only happen once. So I have x equals a -2 twice, and then x equals a +1. So I get x plus 2 times, and then I get an x minus 1. I'll go ahead and multiply those two out. So I get x plus 2. And then this is going to be an x squared. This will be a -x and a +2x, so just a positive x. And then 2 times a -1 is a -2. Got a lot of terms on this. We'll have to do some combining for the next part. Send the x through. I get x cubed plus x squared minus 2x, and the 2 through, plus 2x squared plus 2x minus 4. That's nice. Those 2 x's go, and I get x cubed plus 3x squared minus 4. And that is going to be at least one polynomial that gives me out those specific roots that are shown. We should technically check these intercepts, but for whatever reason, we did not really explore that idea in this textbook. So we're officially done with that question. 14, list all the possible rational roots. So just list them, don't check them. So you want factors of this, factors of your constant, which is, oh goodness, positive and -1 times 26, 2 times 13. That's all I can think of. I think that's all we have. And then factors of your leading coefficient, which is a 1 and a 2. So take these and then one by one divide them by all of this. So positive and negative, 1 divided by 1, 26 divided by 1, 2 divided by 1, 13 divided by 1. Now send the 2 through. 1 divided by 2, 26 divided by 2 is 13, so I don't have to put that again. 2 divided by 2 is a 1, so I don't need to put that again. 13 divided by 2, and I have 1, 2, 3, 4, 5, 6. So 12, because I have the positive or negative possible roots. So one of those, hopefully, will be our winner. If you were going to check them, but we're not. So yay for that. We are going to have to do that, though, in number 15, so I am actually going to go ahead and stop this a couple minutes early so that we don't run out of time, and so we'll pick up 15, 16, 17, and I think 18, right? 18 in part 3.